More Year 12. Today we're going to start with a look at amines and some of their reactions. So their reactions, it's not too complicated really. It's taking nucleophilic substitution, one of your classic Year 12 ones, and just sort of you're using it in a slightly more complex examples, but actually the mechanism is exactly the same. But actually we're going to be thinking about how electrons move around and inductive effects today. So it's kind of a different, almost more like inorganic chemistry, thinking about how sort of the electronegativity affects each other and stuff. So we're first going to see what amines are though. So there are three different classes of amines and one other related thing that we need to know. So we've got one R group bonded to a nitrogen and two hydrogens and has a lone pair. You've got two R groups. Then you could have the nitrogen bonded to three R groups. Now, all of these are all amines. So these all are types of amines. And you need to be able to sort of categorize them just like we would with alcohols. So in alcohols we have primary, secondary, tertiary alcohols. For amines we have primary amines, we have secondary amines, and we have tertiary amines. But it's done in a different way, and actually I think it's far simpler, the amines, than the alcohols are. So in the alcohols, to determine the class of alcohol, you'd look at how many carbons were bonded to this carbon, the one that's bonded to the OH group. For this, we just look at the nitrogen. Much easier. It's just how many are bonded to the nitrogen. So this one's got one R group, one carbon chain. So primary, two R groups, secondary, three R groups, tertiary. They can all be the same. They can be different. They can be a mixture of all sorts. And the final one, it's not really an amine, but it's related, is this, where we end up with four R groups. Now to form this you need to use up the lone pair, and so it's not actually neutral. It's got a positive charge, and you'll often see that paired with like a bromide or a chloride ion, but this is a quaternary. So quaternary going from primary, secondary, tertiary, quaternary, so sort of meaning like four in some way. Ammonium ion. So there's a quaternary ammonium ion. So the ammonium coming from like nitrogen and hydrogens being ammonia comes from that sort of root. So those are the different classes of amines, and then the quaternary ammonium ion, or if you pair it with like a chloride, it'd be the quaternary ammonium salt. Now one of the first things we need to consider is the basicity of amines, so how effective they are as bases. So if we just, I'll just draw out, we'll do methyl amine. This molecule is basic in that to the base because we've got this lone pair that can be donated towards some sort of hydrogen. So that hydrogen can come from any sort of acid. So it donates electrons towards the hydrogen, forming I don't know why I did a nitrogen or carbon. So which forms that. So if let's say that it was hydrochloric acid, we'd form. Now this would be called methyl ammonium. So this is the methyl ammonium ion. So it's like just a nitrogen with one methyl on it. So it's methyl ammonium chloride, because our counter ion, our negative ion, is a chloride. So in this it's acted as a base, the HCl is acting as an acid, just a basic acid-base reaction. But the mechanism for that is that lone pair is donated towards the hydrogen. But what we need to do is compare the basicity of the primary, secondary and tertiary amines. We need to think about which of these is the strongest base. And so we need to reflect back on this and see, right, well, as a base it's donating away electrons. So the more available those electrons are to be donated away, the better the base. And the more reluctant it is to give away those electrons, the worse it will act, the worse space it will be. So anything that affects the availability of that lone pair will affect the basicity of that amine. So we need to then actually have a look back, because we're going to pin this to something we did back in the year 12 content, where we were doing electrophilic addition. So when we looked at the reaction of, let's do propene with HBr. Now, this reaction was, it formed two products, major and minor product, and one of them, the major product, we used a lot more of, and that came down to the two different intermediates that we could form. So, we've got the first stage of the electrophilic addition. If we attach the hydrogen onto the carbon on the left, we end up with this secondary carbocation. If we attach the hydrogen onto the carbon on the right hand side, we ended up with this primary carbocation. Now if we remember back to the reasoning we used, we said that the reaction product from this was the major product. This is not, we don't call this the major. The product it goes on to form is the major, and this one was the minor. And the reason why is that most of the reaction goes this pathway, so like 70%, 80% of it goes in this direction, because it forms a more stable intermediate. Now the reason it formed the more stable intermediate was down to the groups attached to the carbon. So this carbon's got two hydrogens and one carbon chain. Now this one carbon chain was able to donate electron density towards the C positive by the inductive effect. Now shifting the electron density towards the carbocation makes it slightly more stable, so lowers the energy down, makes it more stable. But over here we've got two carbon groups that are able to carry out the inductive effect, so it's even more stabilised by the inductive effect, so more of it goes this direction, so we have a more stable intermediate. If we look back at here, we don't have sort of carbocations, but we've still got these R groups that are able to sort of shove electron density around. So we can donate electron density towards the nitrogen, increasing the electron density on this nitrogen in the centre, and so making it more basic. So a really, really common question you're going to get is to compare the basicity of some sort of primary, secondary or tertiary amine to ammonia. You're not going to get asked to compare primary to a secondary, or a secondary to a tertiary, or a primary to a tertiary, because there's actually a bunch of other things going on that affects the basicity. And so just using the principles we're using here, you would assume tertiary is the most basic amines, and that's not always the case. It's not something, to be honest, I fully understand. I've probably learnt it at university, I've forgotten it. But fortunately for you, all we're going to have to do at A level is just compare ammonia to one of the either primary, secondary or tertiary amine. When we get to some benzene chemistry, we'll then compare it to aromatic amines, but we'll leave that until we've studied what aromatic compounds are. So, looking at this, we've got NH3, which ammonia, just consider that the sort of baseline. In let's say that R is a CH3. This is methyl amine. In methyl amine, we've got the inductive effect of that CH3 group donating electron density towards the nitrogen. Now, we need to make sure we get our language correct in this. So, if I was asked to compare the basicity of ammonia to methyl amine, and I need to explain my answer, first I'm going to say that methyl amine is more basic than ammonia. So that's going to be one of my marks. I've correctly identified that the methylamine is more basic than the ammonia. So the reason it's more basic because the alkyl group, so alkyl referring to methyl, ethyl, propyl, butyl, any sort of carbon chain, donates by the inductive. So that's my first point. So I'm saying that this alkyl group, which in this case is the methyl, donates electron density towards the nitrogen, and that takes place via the inductive effect. Then